Hello everyone and welcome to this introduction to the WaveDev software. In this first video I'm going to talk about some of the main features of this prototyping tool for working with signals processing. So I hope this information can be useful for people who are interested in this field and want to explore different programming techniques. Without more further, let's begin answering the most important question. What exactly is WaveDev? In essence, it is a graphical programming environment, based on processing blocks, arrows and some virtual instruments for the manipulation of signals in real time. Basically, with this tool you can test your DSP algorithms without the needing of writing code. By using a graphical description such as a block diagram or scheme, you can define the processing stages for your signals and get reliable results before implementing them in real DSP hardware. So this can help you to save a lot of development time. You can play with circular buffers, waveform generators, test digital filters and monitor all signals simultaneously with a few moves. The sound card is the primary signal gatherer since it provides a stable sampling frequency, but there are other options to acquire signals from asynchronous sources. For each input sample in the capturer buffer, the entire diagram will execute to process the corresponding output, which you can transfer then to the playback device. So if the sampling rate is for instance 44,100 Hz, your CPU will execute this diagram 44,100 times per second. With that said, let's take a look at the interface and put into practice some examples. This is the main workspace. The interface is pretty straightforward and the concept is similar to many graphical languages. Blocks representing different operations and connected each other in the way that express the sequence of our algorithm. In this example, I have a signal generator connected to the oscilloscope. These types of blocks have their own control panel so we can configure them individually. And then we have this other type of blocks which we can only control through their nodes. In this case, it represents a mathematical function. To find out what this function does, I will put this block between the generator and the instrument. And we also gonna need a variable here to control the function's parameter. So this is what we got. By moving the variable, we can see that the signal is acquiring a more stepped appearance, like if we are transforming the signal to low-resolution representation. I'm gonna show the control signal too on the oscilloscope so we can see the influence of this value over the waveform. Let's apply this function to a more dynamic signal. This time, I'll use a wave file player to send music data to the function. And we can observe the same effect. As we increase the divisor, we start to see a discrete shape of the wave. This time, I'm going to send this signal out to the speaker to hear the result with my ears. Now I'm gonna change the function with another one called circular buffer, to create a single delay. Like the previous function block, we have the signal input, and a single parameter, which in this case correspond to the index, so I can use it to recover any past sample value. To perceive the delay effect, I'm going to add both signals to the output. So let's hear how it sounds like. What about using two delays? For the following example, I will apply a simple low-pass filter to the same music, but I'm going to use probably the most leading feature of this software, which is the ability to integrate other schematics into the current project. In the same way that we call functions in written programming languages, we can call any scheme file and reduce it to a single block. In this case, I'm encapsulating this diagram which represents the filter's mathematical equation. I can skip the theory behind this for a while and focus on the external nodes. These nodes will be reflected outside the scheme. So I can bring external signals here, process them, and export the result out to feed external blocks. So just like previous functions, I only need to set one parameter, which is the cutoff frequency, and we are ready to go. Now let's examine this filter more carefully. With WaveDev, you can create utility schemes to test other schemes. To illustrate this, I'm going to call this diagram, which generates a sine wave in a frequency loop, to feed digital filters and get their frequency response. It uses an incremental counter to sweep the frequency of a wave that we're going to filter then and make the comparison. With the help of this other instrument, we can contrast both signals, the original and the filtered one. If I change the control variable, you will note the differences in the decreasing speed. I'm going to use the same example to test an FIR filter now, and to set up this filter, we will need to specify some kind of coefficients. I have here 203 coefficients that I got from an online filter design tool. With a few parameters, you can generate these lists, and to use these lists in WaveDev, you only have to put it all in a simple text file which you load later with the tap-based filters block, used for both finite and infinite impulse response filter. After loading the file with the coefficients, we are ready to activate the filter and compare it with the previous one. Here, you can see the typical ripple of this kind of filter. Although I cannot adjust this one, it offers a better response than the low-order filter. If you need to use a flexible filter without dealing with the theory, you can try this pre-defined second-order low-pass filter. I will include it here to compare it with the others. To finish the concept of this example, I will show you very quickly these 4 nonlinear amplifiers that I will use later. Unlike the filter test where I used a variable frequency generator, now I'm using a variable amplitude generator to show the magnitude response of these blocks. Together with this instrument, I can visualize the gain curve for each amp. And with the help of additional parameters, I have total control over the shape of each curve. So that's all for this video. This was just a general overview for introductory purpose. The elements shown here will be some of the building blocks for our projects with DSP. You can download a fully functional version of the software in the link on the description below. We are going to learn to use specific software features in the next tutorials. So, if you want to know more tips about this software, stay tuned for future videos. Thanks for watching.